Welcome back to the last video of this week, where I plan to talk about examples of using the theorems we had for this week. So in particular the convolution theorem, which is a way to talk about the connection of the random walks on the groups into products of complex numbers, what we have here. So let's talk about the examples, basically what I want to do here. So let's take the standard example we have talked about already several times. So what we have here is that let's take this half Dirac at 1 plus half Dirac at -1, and take this in, let's say, in ZP. P is at least 2, and now I don't know if you recall, but we computed the Fourier transform of this already. So if we take the Fourier transform at k, then using basically the fact that this becomes like a complex numbers, but I recall it just briefly. So this is minus 2 pi I k over p, and then plus half 2 pi I k over p, so that's at the -1. So this becomes then a cosine using just the identities for the cosine 2 pi k over p. That's the expression. So it's a real number, so it's some real number. And what we now can do is that now if you start to take a convolution, let's say with itself, we can then now study this convolution power. So we can take now first the Fourier transform of this and take this at the point k. Then by this definition, if we open this up, we get by the convolution theorem, so this is the convolution theorem, we get that this is equal to the Fourier transform of k and then Fourier transform of k. And now if you take the power, you just take the cosine to the power 2 pi k over p, as we had here, to the power 2. So just studying the cosine powers, you can get into the Fourier transform, like understanding what these Fourier coefficients are. And in general, we have, of course, if you take the iterated convolution n times, which is kind of defined the long-term asymptotics of the random walk at the point k, then it's just cosine 2 pi k over p to the power n. So the usefulness of this now, that if you see that you are fixing k and you are fixing n, so if you think about these cosine numbers here that we see here, okay, let's just draw kind of the picture we have here. And at different points k, so we have with k is equal to 0, maybe k is equal to 1, and k is equal to 2, and so on. So we have different numbers here, and that's equal k is equal to p minus 1. So that's all the things we have here. And if you take the cosine powers, like I could take, for example, maybe the absolute value of this, if I wanted to study this a little bit, then it becomes an absolute value of this, so it looks like something of the value. Then the cosine function is some oscillating function. So when the k is increasing, so when k is quite large, we have like different values of the different k over here. And it depends on whether we reach the point 1. So the 1 is here kind of the thing that we have here, which is turns out to be later on that this is kind of the danger point, that we don't want to reach the point 1 too often. And once you study the k, then the hope is that, okay, if you take k is equal to 0, of course in this picture we get the point 1. So that's the k is equal to 0. So that's the value of the function, the Fourier transform of k. So this is the, I'm just taking this is the graph of the Fourier transform of n and its values. And then once you start to look into this, and k is equal to 1, okay, it depends on p. So it depends on what p we are using. So you can see that there's actually a p dependence, that whether it's, let's say, a prime number or something, then you might think that whether k divides this. We know that k is between p minus 1 and p, but it might depend on really the values that we get here. So hopefully we get something like this, that okay, this might maybe oscillate something like this, I don't know, in this way. Of this type. So this might look something like this, for example, the graph of this convolution power. But the important thing here is that there's this power n. So you can see that these lengths, so some of the lengths are like getting really small. So these get like very small if this cosine of 2 pi k over p is small. So if already this is small, like this absolute value, so it's not equal to 1, so it's actually not so small, but if it's just less than 1, then these will get exponentially small. They get very small very fast when n goes to infinity, because it's an exponential sequence. So it turns out, later on we will see, this is like the kind of the foundation of the course, is that when these powers get very small, you can actually then think about it, the faster this, let's say if like our aim would be, for example, to prove that this mu star n, let's say, converges to uniform distribution at 0 with quite fast rate, and this is connected to how fast these powers, this mu star n convolution powers at k, converge to 0 as n goes to infinity. So once you take the larger and larger of these convolution powers, then you can actually connect them to these rates of these things. So that's what you can see in this example already, that we see this like shrinking of this size. And later on we will see, when we use the Plancherel's theorem and convolution theorem together and Cauchy-Schwarz inequality, we can actually make this kind of precise. But already this example shows that somehow very quickly from the convolution theorem we get this information about the mu, which just as a product. So we get this into a product to the power n. And maybe another type of an example, which I want to maybe talk about as well. So let's talk about this other example. So what if you have like a different measures? So we have, let's say, mu1 and mu2. Maybe this is an example 2, and that would be an example 1. And we have sequence of measures. So these are all probability distributions from ZB, probability distributions. And now we have this idea that, okay, yeah, so now we can take their convolution, mu2, mu3, and so on. Maybe I can take n of them, mu n. So what this would correspond as a random walk question is that now you have a situation where at every stage, let's say we start from the first point that we have certain like a random walk, and at the first step of the random walk we, let's say, go to somewhere with different probabilities, and we choose this with the probability mu1. And once we are in the second stage, let's say over here, then we choose like where we go from here with probability mu2. So somehow the choices, like after this, like after you choose, like let's say from here and here, this is a mu3, might change on every step. But still, you can do the same kind of analysis in this kind of situation. That now let's write the definition. Let's call it nu n. And now if you take the convolution theorem, you take nu n and take its convolution at the point k, then again we get this into a product. So this becomes, by the convolution theorem, as a product. If we take, let's say, I could take from j from 1 to n, and then you take mu j, take its Fourier transform at the point k. So it's very similar to like what I did had the previous examples, but now you can see that even if you have different distributions, you can still analyze the full random walk. We can get into the same kind of picture like we had here with these bars, that we can like think about it, okay, whether like, for example, this would converge, whether like if the nu n would converge to the uniform distribution, is then connected again to this product. So this becomes a bit more complicated question. So you need to compute the Fourier transform of each of these probability distributions simultaneously. But as long as you can control their common product, then you can get information about the limit distribution. So of course, if the if they are the same, then it reduces to the previous question, becomes exponential growth. But it could be that, for example, maybe these mu j's have maybe a spectral gap that maybe shrinks over size. So, for example, something of that type. And that's like a valid question. So sometimes you might have that kind of situations. And we will later on see that there will be examples in group theory and actually in graph theory where there are like different distributions at every stage, but there will be some uniformity over the sequence. And once you just have the uniformity over the sequence, as long as it kind of makes this product that we have here like converge, or converge, let's say, to zero, for example, then you have enough like decay to get the, let's say, the convergence to the uniform distribution. So that's one of the like important bits about the convolution theorem. It allows you to do this kind of analysis for this kind of several products as well. And in the next week, I want to talk a bit more about more applications of the convolution theorem. So these were just like kind of simple applications, but they were very important because this is exactly how we will apply soon the convolution theorem to getting the distance to the uniform. So just wait for the next week and you will see how this whole machinery now comes together by putting all these things together and getting this theorem. So I will return to these two examples just in the next week's videos, and you will be able to see like how important they are with the theorem. So that's all for this week, and thanks a lot.